That's fair. Is this the one where you had to design an experiment? Was that on this one?
Yeah.
Yeah, they do that. It seems like they do that every 5 or 6 years. I don't know. I don't know. I wish we'd done more lab work. That's like the one thing that I feel like I really dropped the ball on this year. Among other things. There are a lot of things, but that's the biggest one. Okay, so anyway. All right, so number one, you've got this spring. So this is, what are we doing, 2012? This is FRQ number 1. So you're given this drawing where you've got a spring. You're told that your equilibrium position is back here for some reason. Our spring has a constant of K. We know that the mass of this thing is 0.3 kilograms. It's placed on a frictionless table. It's attached, blah, 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 blah. It is set into oscillatory motion by stretching the spring and releasing the block from rest at time t equals 0. So your initial position is greater than 0, right? And I believe that that is important later on. Okay, so is everybody good with that? So we're going to pull it back, hold it at rest, and then release it. Good? All right. What's our starting velocity, you guys? 0, right? Okay, let's see. The resulting graph of v versus time is shown below. The positive direction for all quantities is to the right. So positive, negative. So that's our drawing and our setup. Is everybody good with that? All right. So, let me buy some space here on the board. Okay, so our velocity time graph is an inverted sine curve, right? So v of t looks like it's negative. Oh, well, this is question A, right? Determine the equation for velocity of time, right? So, so for part A, velocity at time t should be v max times the sine of omega t plus some phi, maybe, right? And don't forget about the negative, right? Because it's inverted. So let me pause there for a minute. Is everybody good with how I got this? Yeah. It is, yes. But I don't think it tells us what x max is. So I agree, v max is negative omega x max. But we don't know our x max. You see what I mean?
Yeah.
Everybody okay with that, with what I've done so far? Yeah. Okay. So, what's v max according to the graph, you guys? It looks like it's about 0.16, right? So, you get 0.16, don't forget to make it negative because the graph is inverted, times the sine of, let's see, I need to find my omega t. So let's see, omega is 2 pi over the period, right? And if you look at the graph, the period looks like it's about 0.7 seconds. And so that gives you, it's like 8.98. Cool? So 8.98 times t, and is there any shifting of the graph? No, it looks like at time 0 our velocity is 0. So check. So no phase constant there. Shoot.
I'm not sure if this is a dumb question, but
Not
can
at all.
you say, I know it's velocity time, so it should be negative anyways, but if you said it was positive, could you just shift it pi over 2? Is that, like, acceptable?
You would have to shift it pi.
Is it just pi? Yeah, pi. Not
Yeah, that would also be acceptable. If you wanted to make that positive and do plus pi, that would also be acceptable.
cool.
All right, everybody good? Problems, questions, concerns? Okay, part B, given that the equilibrium position is at x equals 0, determine the equation for x of t, including numerical values. So, this was all part A. So part B wants to know an equation for position at time t. So in general, and it looks like we're mapping up here, our position at time t should be x max cosine of omega t. So I already know the omega t. All I got to do now is find my x max, right? So how do we find x max? Sure, we got to.
You know that Vmax is equal to X max times
Yeah, we know Vmax, so we can find x max, right? Because we know our omega, right? Did anybody try to take the integral of this mess? You can do it, but you're making your life way harder than you need to, right?
No, well, I did something even dumber. I found k first, and then I found x max using EPE is equal to ke.
Okay. Did it work?
Yeah.
So yay, physics, right? And the easiest way to do it is to remember this, right? Follow? All right, so based on that, then it looks like our x max is going to be Vmax over omega. And it gives you, I got 0.0178. I'm getting cocky here. I haven't been checking my answers, which is bad. So anyway, so plug your numbers in. Sure, if you do 0.018, I think that's fine. All right, everybody good?
It says we'll get yelled at if we do point or 4.
They seem to be really lax about sig digs on this physics test. Like, I would not stress about that.
Calculus, they're really strict. Okay, that's-
Yeah, I don't know, it's weird. All right, so are we good? All right. Part C says calculate the value of K. So, K is just m omega squared, right?
Oh, that works. Okay, sure.
Okay, sure, like I believe that, or okay, sure, I knew that but forgot, or
Yeah, or t equals 2 pi root O.
sure, you could do, yep, you could do t equals 2 pi root m over k and solve it that way. Good, you guys? All right. So that's part C. Any problems up through part C? Everybody's happy? Okay, experiment number 2. The block in the spring arrangement is now placed on a rough surface, as shown below. The block is displaced so that the spring is compressed a distance d and released from rest. I don't know why they switched it up there. That seems really arbitrary. But so here is our new drawing for parts D through E. All right, and it's released from rest. So it says on the dots below, draw and label the forces, not the components, that act on the block when the spring is compressed a distance of x is d over 2, half of d, and the block is moving in the direction indicated. So the first dot represents when it's moving back towards the equilibrium point, right? So that means to the right. Okay, so the forces you should have. Gravity, which we've all agreed we're going to use mg to represent. There's going to be a normal force. What else, you guys? Sure.
Just a question. Wouldn't it be negative mg since g is a constant?
Usually when you make these drawings, this just represents the magnitude of it.
Okay.
And the arrow shows the direction. It wouldn't. I don't think you would lose any points if you made it negative, though. You know, I mean, it's.
So on that note, when we're doing the friction and the spring forces, we shouldn't label either of them as negative then, and just leave as arrows?
That's what I would do.
Okay.
But again, I cannot see a circumstance where they would take points off of that.
Okay.
Yeah, because that already makes sense.
Everybody good up to there?
Yep.
All right, 2 other forces. What do we got? Give me one, Justin.
Spring.
The spring. Which way is the spring going to be pushing everybody? To the right, yes? Because it's compressed this way and it doesn't want to be compressed, so it's going to push to the right. So here's the force of the spring. And one other force. Friction. Cool?
Do the lengths of those friction and spring matter here?
I don't think so. I think you could fairly safely assume that the force of friction is less than the force of the spring. Otherwise, but I don't know. What does the rubric say? I don't think it says anything about the length. Let's see. Question 1. What do we got? Part B. Let's see. So let's see. Points are given for drawing and labeling Fn and Mg correctly. Yeah, it doesn't say anything about the length of the arrows. Yep, oh, notes. Length of the vectors is not considered only direction. All right, everybody good with this one? All right, how is it going to be different for the other dot where the block is moving away from the equilibrium position? Everything is the same except friction goes the other way, right? Because remember, friction opposes motion. Yes, sir.
I did it in a way where it's past the equilibrium point and it keeps going. So it is technically moving away from the
Gotcha. But so if you read the thing for part D, it says on the dots below, blah, 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 and then the word compressed is underlined.
Oh.
Okay, so it couldn't be over here. It's got to be over here. Capiche?
Yeah.
All right, everybody good up to there?
Yeah.
All right, now E. So this is weird. I need to look again at the requirements. I don't. So in part E, we've got simple harmonic motion, but now with damping. Okay, did we talk at all about damping? I don't know if we did. I know I talked about it in my honors class. I don't think I did here. Why are you guys making funny faces?
We had a test.
We had a test on it today.
Oh, did you really?
Yeah.
Gotcha. So I need to look again. I don't remember seeing it in the requirements, but obviously it's here. All right, so here's what you need to know. So all of the simple harmonic motion that we considered is ideal, where you're not losing any energy. So that it's sort of a perpetual motion machine, right? But in the real world, there's going to be friction, air resistance, those sorts of things that are going to impact the amplitude of your oscillations, right? Everybody good up to there?
Yeah.
So it turns out when you have a damping force, whether it's friction or air resistance or whatever, it turns out the only thing that it affects is the amplitude of the vibrations. It doesn't affect the period, it doesn't affect the angular frequency, it doesn't affect anything except the amplitude. Follow? So, it asks you to draw a velocity versus time graph. Well, our original velocity versus time graph, looks like this, right? So our new one should look the same, except the amplitude should just get smaller and smaller as you go. Follow? And the only other difference is your initial velocity needed to be positive, right? Because we compressed the spring and released it. So the initial velocity is going to be this way. Okay? So for part E, here are the things that they're going to look for. They're going to look to make sure that at time 0, your velocity is 0. Right? And then when you release it, the velocity becomes more positive. Cool. And with each oscillation, the amplitude should get less and less. I didn't give myself enough room to draw this, so I'm going to backtrack. Something like that. Cool. And your period should be 0.7, and this intersection should be half of that. Yes, sir.
Okay, so in situations with springs where the restoring force is not proportional to the displacement, can you use the period equations that we know for simple harmonic motion?
No.
So, but wouldn't that be like, so if the restoring force wasn't proportional to the displacement, like that one that we saw where it was like a spring where it was like this and it
Right.
went like that, so would the period be different then?
Yes.
Okay.
Yeah, and deriving that would be significantly more complicated. And I don't know that you're expected to be able to do that. Cool? Yeah, yeah. So all those equations that we learned from this chapter are for simple harmonic motion. All right, does this all make sense, you guys? Okay, so I need to make myself a note that I do need to do damped simple harmonic motion next year, as if that simple harmonic chapter wasn't already hard enough. We had to
Wait,
tack
that's-
on one more thing.
That's position time, right? Not velocity time?
No, it is velocity time.
Okay. Okay. Thanks.
Do you see why or no?
Yeah, no, I get it.
Because your initial position would have been negative, right?
Yeah.
Because you had it compressed a distance of d and then you release it.
Okay.
Follow?
Yep.
All right, is everybody good? Yep, so, and then, yeah, oh, Justin beat you by half a second.
I still don't understand why it's not moving to the right after the equilibrium position. I know Adam asked that, but I still don't.
Wait, say that again?
You say, for the second dot, I don't understand why that the force of friction is, or why it's not moving to the right still.
It was the same thing as what I asked.
Yeah.
I know.
Right. So it says on the dots below that represent the block, draw and label the forces, not the components, that act on the block when the spring is compressed. So it's got to be at this point compressed, not over here, but over here, because over here it would be stretched, right? Not compressed. Okay.
So
And it's moving away from the equilibrium point. Wait.
I understand now. I misinterpreted the question.
Moving. Yeah, and moving away from the equilibrium point would mean it was moving this way.
Okay, I understand now.
Follow?
I thought it was I thought it didn't really, the position didn't really matter for the second one and it was after it, but it's supposed to be at the same position.
Correct.
Okay.
Yeah, so the idea is it hits this position twice. Once as it's moving away from the equilibrium point, and then once again as it's coming back towards the equilibrium point. So the first dot is this guy, the second dot is this guy.
I understand that.
Everybody good? Oh, Zach, you had a question too.
Oh, yeah, I kind of answered it myself. I was just wondering what the position time graph would look like.
For this?
Yeah, so I was thinking, oh, maybe the periods changed, but that's not right. So it's just the amplitude is getting smaller.
Correct. Yeah. So you would start at a position. So if this was position, your position would begin at negative d, right? At rest, so that means my slope needs to be horizontal, right? And then when your velocity is maximized, you should be at a position of 0. So it should do something like this. All right? So that would be your position graph. Make sense? All right. Questions on that one? All right. So are we good with the damping thing? The only thing that changes is the amplitude if you have a damping force. Cool? Awesome. All right. So that was number 1. So number 2. All righty. Okay. So this is about experiment design, and like I say, this is a thing that I did not do a great job prepping you guys for, and I apologize profusely on this. So basically what you need to do is, using the equipment there, you need to design an experiment that tests whether or not there is genuinely conversion from gravitational potential energy to regular old kinetic energy. Cool? So when I read it, I thought of basically 2 different experiments. Anybody have an idea of how you could set something up? Sure, we got it.
I did the cart and the track.
The cart and the track. So describe the track.
So the track like starts high and then goes down to the left.
Okay, so inclined plane, right? As the cart rolls down the hill, you should be converting gravitational potential energy to kinetic energy, right? Please make sure, if that was your answer, that you are careful. How, in that instance, how would you find that final velocity to find the final kinetic energy? Can you walk me through the process that you would use?
I thought about that while I was doing it, and I was like, well, they might just have...
So you can do it in 2 steps, but it's important that you guys know how to do this.
Stop.
Okay, so you've got a stopwatch. So what are you going to use the stopwatch for?
To time how long it takes to get from the top to the bottom.
Okay, so you know how far it rolls down the ramp. You know what's called that distance d. And you know the time that took, so you can do distance divided by time. Am I done? I got you. Give him a second.
I would have just... No, wait.
Okay, so let's talk about that. So if you do this, and this is cool, like your setup is good, but you also have to know how to do the calculations. So what you're telling me is that the cart is going to roll through a distance d in a time t. So if I do distance divided by time, does that represent the final velocity? You're shaking your head. What does it represent?
Represents average.
That's the average velocity. Cool. How do I then connect that average velocity to the final velocity? And this might be the piece you're missing. Yeah? All right, McKeever, you had a hand up. Were you going to help him fill in this blank here? Okay, let's finish this before we get there. What do you got, Seba?
VF plus VI over 2.
It is VF plus VI over 2. And what's your VI? 0. Why is it acceptable to use this VF plus VI over 2 equation? Acceleration is constant, right? Cool. So then you know your final velocity. Now you can find your kinetic energy and compare your GPE to KD. Good? Other questions about this specific experiment design? Going once? Twice? Okay, McKeever, you had a question.
I had a question. I literally have a couple of ways that I could see to find the velocity, but I wasn't sure which ones, if they were valid. Because if you use, like, for instance, if you use G and the angle to find the velocity based on the time, like, you know how you have the predicted velocity from the energy, but would that also count as a predicted, or would that be experimental? Because if you use, like, sine theta G times t squared divided by 2 times m, that's one way. I think that's one way to find the ke. It's 1/2 mv squared.
But I don't think that's experimental, that's predictive.
Okay, but then what about 1/2 2x? So 1/2 and then quantity 2x over t squared times m
1/2 quantity 2x what?
over t.
Equals what?
Well, the 2x is the t is in the parentheses.
Equals what?
I think that's also. I don't really know. I didn't write that down.
I don't know what this equation is.
Oh, that's
Or if
the
it's
outside.
inside or
Maybe.
Oh, this is your, I mean, this is units of velocity. I think that's the same as, well, okay, so let me say this. In order to use this, you'd have to measure the time
Yes.
experimentally,
Well, like stopwatch. Yeah.
right?
Yeah.
So that's good, but I don't think this equation is right, because this just gives you d over t. This is your average velocity again.
No, it was like I did 2a delta x. Wait, no, I didn't do 2. I don't really know what. Oh yeah, the
Are you-
Hernando equation.
Are you trying to do this guy?
I did the Hernando equation. Yeah.
Yeah, that works. So this would be your d,
And
and your
then-
vi is 0.
Yeah.
Yeah, that works. That's the same as this.
And then I plugged that into the kinetic energy.
Dynamite.
Okay, so that
Yeah.
works.
Perfect. So, but the point is, in some fashion, you need to experimentally find that velocity at the bottom. And it's tough, right? Because your velocity is changing, and there's no way to use a stopwatch to get an instantaneous velocity, right? So your best bet is to find an average and use that average to find the final. Cool?
Are we only allowed to use one of each item on the checklist?
Oh, I don't know.
Didn't say.
No, you could use multiple. Yeah, because one of the setups involves using multiple cards.
Okay.
So yeah. Okay. Yes.
How are we supposed to draw a meter stick in? Would you like
Rectangle.
measuring it?
I don't know. I mean, I would look at the grading scale. I don't think you need to.
This is measured.
3 points for artistic ability.
Yeah. This is one where I would definitely defer to the rubric, and see what it says. Yeah, they don't even have the meter stick drawn in their solution, so I think that's fine. I think it's within reason. Okay. Let's see. Did anybody come up with another solution? Okay. Cool. Oh, yeah.
It's kind of the same as this one. I started it off on a flat track and you use a meter stick and a stopwatch to find the initial velocity, and then it goes up an angled track, so you can find the height that it goes to.
Oh, I gotcha. So that is super cool, but I don't think it satisfies the expectations, because the experiment you just described transforms kinetic energy to gravitational. And the wording of the problem, it says experiment involving a transformation from initial GPE to KE. So your translation went the wrong way. But you could do this,
You could say the part.
and then you just reverse it and find the average velocity down here and assume that that's the same as the VF.
You could say the part when it's falling back.
Right, or coming back down, yeah. All right, good? All right, there is another solution that involves using a system of pulleys where this would be your initial setup. I'll do this real quick because most of you don't care. So that would be your initial setup, right? And then you release it.
Why would you do that?
So you've converted the GPE of this weight to kinetic energy of the system.
Okay.
Then it all falls.
Cool? All right. Let's see. So that's A and B and C D. So this is a weird question. It says, after your first trial, your calculations show that the energy increased during the experiment. Assuming you made no mathematical errors, give a reasonable explanation for this result. So, my knee-jerk reaction was, I would have probably just written, well, that means that my reaction time is too fast in using the stopwatch. And I legitimately don't know if that's an acceptable answer. The answer they gave was that you may have given the cart a gentle push when you released it. Which to me...
But that's not,
yeah, I know. Because like in my mind, it's like, well, put something in front of it,
yeah.
and then pull the thing out, and then there's no way you push it, right?
And then you still don't end up with more energy than you started with. You just gave it that energy to begin with.
Well, right, but you didn't account for that when you
just
did your
didn't calculate it.
calculations.
But that's a mathematical error, right?
Oh, right.
So they,
Sure, yeah. So, I feel like the time one would probably be okay, but
Yeah.
I don't know.
In moving something away, you created a pressure indifference,
Oh.
so that actually sent it forward.
You're actually right. That's true. Yeah, Bernoulli. Yeah, A+. Good. I'll let them know you don't need to take the test on Monday.
Oh, so it is on Monday. I couldn't remember what one.
All right. And then E, this one to me made way more sense. On all your other trials, the calculations show the energy decreased. Why would that happen? One word. Friction that you didn't account for. Cool? When you answer that, describe to me, friction is an important type of force. It's a non-conservative force. I think you need to state that in your answer. Friction is a non-conservative force doing work on the cart as it goes down the inclines, and thus you lose energy. Clear? All right. Oh, yeah. Oh, good. So it gave you that lead. Thank you. All right. Everybody good? All right. Finally, number 3. We had almost this exact same problem on a homework assignment. I don't know if you guys remember the bowling ball problem. It was like, how far did it slide before it begins rolling? So you have seen this problem before. All right? Now, that being said, it's not an easy problem. All right? But let me just say this. Well, I'm getting ahead of it. All right, so here we go. Number 3. So you've got a ring with a mass of m and a radius of r. It gives you the equation for the rotational inertia. It's initially sliding on a frictionless surface at a constant velocity v naught, blah, 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 and then it hits this friction portion where the coefficient of friction is mu. Part A, starting from Newton's second law in either translational or rotational form, as appropriate, derive a differential equation. I don't know why they wanted you to go differential on this. They're making it more complicated than they need to. All right, so let's finish reading through it and you'll see what I mean. So it says, derive a differential equation that can be used to solve for the magnitude of the following as the ring is sliding and rotating. So Roman numeral I wants to know an equation for the linear velocity of the ring as a function of time. So we're trying to come up with an equation for the velocity as a function of time. All right, so let's make a free body diagram of this. All right, so here's the ring. What forces are on it? Well, two obvos are gravity and normal force, right? And what other force? Friction. Anything else? Torque isn't a force. You're good to be thinking about torque because it's going to be important here, but that'll be important when we get to the angular part, Roman numeral 2. All right, so does everybody agree this is my free body diagram? All right, so net force equals net force. Mass times acceleration equals force of friction. Negative. Don't forget that negative sign. It matters there, right? Follow? All right. Let's see. We don't. The variables that we're allowed to use are m, r, v naught, and mu. So I should replace this, right? So this becomes ma equals normal force is mg times mu, right?
So you didn't have to specify whether it was kinetic or static?
That is a good question.
It didn't.
It's sliding, isn't it?
It's sliding. I mean, I don't know. I don't know if they give points for that. Anybody notice that in the rubric? Were you given points for identifying that it was kinetic? I don't think so. Yeah, nope, not so much. Okay, so is everybody good up to here? Any problems? We're almost done. Why am I happy? Mass is canceled, so now we've got this. Okay, now it wants a differential equation. Oh, well, A is dv dt. There you go. Cool? Any problems with Roman numeral I? Roman numeral II. Same thing, but now we want angular. Yeah. I can. Maybe. All right, so now, Roman numeral 2 wants an equation for the angular motion, right? So now I want to be thinking about torque. So which forces are providing torque? Just friction, right? So here I did net force is net force. Here I'm going to do net torque is net torque. So MA becomes I alpha. Net torque becomes the torque from friction. Cool? So let's see. So I is mr squared. Alpha is alpha. Torque from friction. Well, that's going to be my force of friction times radius, right? Because my pivot point is the center of the hoop, right? Positive or negative?
Negative.
Is my angular velocity going to increase or decrease? What's the angular velocity at the beginning? 0, right? It's just sliding at the beginning, right? Okay? So you've got to gain angular velocity. Don't worry about, I know what you're thinking, but I guess the point is your net torque and your, how do I want to say this? Here we know that our acceleration, our linear acceleration has to be negative because you're losing linear velocity, right? Similarly, our angular acceleration has to be positive because you're gaining angular velocity.
Regardless of direction? Or?
Yeah, so I know what you're thinking. You're thinking, oh, that's clockwise. So if you want to do it that way, then you would have to make, you'd make both of these sides negative, right? Because your angular acceleration and your torque are in the same direction. So the negatives cancel. Okay, so let's see. Some stuff here cancels out, right? Let's see. I'm going to lose an M and an R. I'm going to lose an M and an R. So it looks to me like R alpha equals mu G, which means that alpha is mu G over R. Now, differential equation becomes d omega dt equals mu G over R. Make sense, you guys, or no? Matt, you good? What's up?
No,
You sound unsure.
I was just, we had to do the beginning part with that torque, once they skip to alpha equals AI.
No, you can't, because it's not smooth rolling.
Oh, yeah, yeah.
Do you know what I mean? So like, as a simple example, at the beginning, your linear velocity is not 0, but your angular velocity is. So V equals omega R won't work there, right? Follow? But that's important, because the point at which it stops sliding is the point at which that does work. Do you know what I mean? So that's what we want to do, is we want to find the point at which alpha, A does equal alpha r, or V does equal omega r. Clear? All right, good. Sebo, you okay? You're really quiet this week. Is everything okay? What's up?
Dying.
Are you? Because of this?
Just general, I guess.
Just general.
Is there anything I can say to help
No.
that does not involve a time machine?
Nope, we're good. Focus.
All right. All right. Everybody good up to here? All right. So here's what we just ended up with. We just had two things. We got dv dt equals negative mu g, and we got d omega dt equals mu g over r. So those are the two equations we just got in parts 1 and 2, right? Everybody good? Okay, part B. Derive an expression for the magnitude of the linear velocity as a function of time and the angular velocity as a function of time. So now we're evaluating these two things. Okay? So how can I get from this mess to v of t? How can I take, so this is, what are we on, B, Roman numeral 1? How can I get from this to this? Integrate both sides, right? So before I can integrate, I need to multiply by dt, right? So you get dv equals negative mu g dt, right? And I'm going to integrate both sides. Cool? So time goes from what to what? Time goes from 0 to t. V goes from, very good, VO to V at time t, right? Make sense or no? So on this side, I'm going to get V of t minus V naught. And on this side, I get negative mu gt. And then add the V naught to both sides.
Was V not 0 in the?
No, because it's sliding when you first release the ball. Oh, sorry, it's not the bowling ball problem, but it tells you it's good. All right. Does this make sense, you guys? Okay. All right. All right. Same process over here, right? So we're going to multiply by t. You guys are not instilling me with a ton of confidence here. All right. So we're going to integrate both sides. So once again, my time goes from 0 to t, and my omega goes from. What's the starting angular velocity of the hoop or wheel or whatever it is? 0 to omega at time t, right? So this guy is just going to give us omega of t. And over here, you're just going to get mgrt, or mgt over r, sorry. Mu gt over r. Cool? Problems? All right, part C, derive an expression for the time it takes for the ring to travel the distance L. Now notice, you're not allowed to use L in your answer.
No L.
Okay? Because if you look at the beginning, it says express all answers to the following in terms of m, r, v naught, mu, and fundamental constants. Okay? So, and this gets back to what Matt was asking about before. What's going to be true when it stops sliding and begins smooth rolling?
It's walking the circumference of the circle.
It's walking the circumference of the circle. So that's when the jumper equations hold true, right? So what we want to do is we want to solve this. Right? So look, I've got V, I've got omega, so I'm going to write an equation. Where can I do this? So I want to write V equals omega r. So VO minus mu GT equals omega mu GT over R. So that's my omega times R, right? Follow?
Yeah, sure.
What happens? Why am I happy?
R's cancel.
R's cancel. Add mu GT to both sides. And then solve for t. Divide by 2 mu g. Cool? Adam?
Why this? I get how it works, but I was.
So, when we talked about rolling, let me see if I can find a thing that I can use to roll. I will use my peanut butter jar. Is anybody allergic to peanut butter? If so, stay the bleep away. All right. Okay, so look. So, right now, this thing is spinning, right? So it has angular velocity, but it has no linear velocity, right? So would it be true in this instance that v is equal to omega r? No. Because there is no linear velocity. There's only angular velocity, right? Here, similarly, now there's linear velocity, but not angular velocity, right? So again, not true. All right? When you first roll a bowling ball, what's happening is it's sliding and spinning like this, right? So you've got this going on and this going on, but there's no connection to the angular velocity as compared with the linear velocity. Follow?
Yeah, I think I get it now because now you found the time where the jumper equation holds true. So
Exactly.
Okay.
Good?
Yeah.
So that's a trick, you guys. Anytime you see one of these things where you've got a thing sliding and rolling, the jumper equation holds true once it's smooth rolling, once it stops sliding and is legit rolling. Yeah.
I would get if I could just see that we're supposed to do that. Say that it said that it's the time it takes to travel the distance L. My mind immediately jumped to equations with L.
I know, I did the exact same thing. How are we
supposed to think of using that instead?
Well, now you know.
Yeah.
Yeah, I mean, I think it boils down to the restrictions of what constants you're allowed to use. So you really, I think the moral of the story here is make sure that you're really careful looking at what variables you're allowed to use and not allowed to use. Does that make sense? I mean, so it gives you a definition of L. It says L represents the distance that it goes before it begins rolling without slipping, you know? And so now it's saying find the time to go that distance L, but you're still restricted to those same 4 variables. Do you know what I mean? Because I started to do the same thing. I started to try to solve it in terms of L, which honestly I think is harder, frankly. All right, everybody good? All right. So then, part D, derive an expression for the magnitude of the velocity when that happens. So now you just take the time that you found and plug it back into your velocity equation. Cool? Everybody good? And then, do you guys agree? So for part E, it says now find L. Do you guys agree that your acceleration is constant? So now you can use any of your kinematics equations. Okay? So I ended up, you know the bell's about to ring here. So for part D, you get that the velocity at the time that it has gone a length L is V0 over 2. Cool? So now to find your length for part E, you can use the Hernandez equation. You know your VF is V0 over 2, your VI is V0, and then your time you found before, that's this V0 over 2 mu G. Cool? All right. So I'm going to stop there. I gave